Yes, hello everyone. Yeah, this morning or this moment, I want to share you again about how to solve some question regarding thermal physics. About thermal physics, yeah, for grade 12 A level, yeah. I have some solve question from this worksheet, yeah. So, okay, let's just continue how to solve this question, yeah. But don't forget before we continue to subscribe my YouTube channel. Please click the button of subscribe. Yeah, like also share to the others. Yeah. Okay, let me start about number one and so on. Yeah. I close my face first. Okay. Yeah. Question one. Yeah. On figure 2.1, place a tick, yeah, against those changes where its internal energy of the body is increasing. Yes, internal energy of the body is increasing. Is it water freezing a constant temperature? Yes. Let's say this is constant temperature. Yeah. On the constant temperature, there is no change in temperature. There is no change in kinetic energy, and there is change in internal energy because internal energy is accumulated by kinetic energy, and then kinetic energy related with temperature. So this is no, yeah. And then a stone falling under gravity in the vacuum. Under gravity, falling stone in the vacuum, there is no particle on this medium, so there is no friction, there is no increasing in temperature, so there is no change in kinetic energy also. Same also, there is no change in internal energy, so this is no, yeah. Then, water evaporating at the constant temperature. Yes, this is about the not as the temperature on the constant. Yeah, this is about evaporating. So they have a work done. Yeah. So on the first law of thermodynamics, there is a relationship between internal energy and work done. So if it change, you are increasing this. Yes, yeah, this increasing also. Internal energy will increasing because work done is decreasing. And then stretching wire at constant temperature. Yes, of course. Stretching wire, they have work done. Yeah. They have work done. Change on also internality, it will change also. Yeah. Okay. Now big question. Okay. This is about calculate. Yeah. A jeweler wishes to harden a symbol of pure gold by mixing it with some silver to get the mixture constant 5.0% silver by weight. The jeweler melts some pure gold and then add the correct weight of silver. The initial temperature of the silver is 27 degrees Celsius. Use the data figure 2.2 to calculate the initial temperature of the pure gold so that the final mixture is at the melting point of pure gold. Okay, we have table about gold and silver. Regarding melting point for the gold is 1340, yeah, in Kelvin or in Celsius. Silver is 1240. Specific heat, yeah, of the gold is 1129 joule kilogram minus 1 Kelvin minus 1. Oh, this is I think this is in Kelvin, yeah, because this is in Kelvin. Also, silver they have specific heat capacity as a 235, and specific latent heat of fusion is 6 to 8, yeah, 100, yeah, 628, and silver is 105. Okay, now I find the first I find is about heat loss by liquid gold. Yeah, the gold has mass as the 90, which one? Sorry, 0.95. Oh, because this is 5%. Yeah. okay, 5%. So 95% is 0.95, yeah, times one. This is specific heat of the mm, gold, yeah, and delta T. And heat gain silver is 0.05, yeah, because this is 0.5% silver by weight, yeah. This is 5% also, yeah. Okay, okay. 200, this is a specific heat of capacity of silver, and change in temperature is 1034 T minus 30. This is 27 degrees Celsius. We change into Kelvin. Yeah, 0.05 M times 10 power 1000, sorry, 150, yeah, thousand, yeah. Okay, okay, finally we get 1 to 2.5 M, yeah, because from here, yeah, uh, delta T, yeah, from here I think this is M, yeah, sorry, we uh, yeah, because 95% of mass, yeah, and we calculate this number into 1747 ohm M. So after we calculated, delta T is 143 Kelvin, yeah. So we can say heat loss by liquid gold. This is something with heat gained by silver. Use the Black principle or a zero law of thermodynamics here. Okay, and the final temperature, yeah, the final temperature is 140 plus 100, 1340. Yeah, because the initial velocity, initial temperature is 1340. So something with 1483 in Kelvin. Okay, I'll go to see. Suggest the suitable thermometer for the measure of the initial temperature of the cold. Yes, this is thermocouple. Yeah. Why thermocouple? Because this is a high temperature. Yeah. We can use the mercury, we can use the other temperature. We need to use the thermocouple. Okay, question 2. The first law of thermodynamics may be expressed in form, yeah, delta U equals to Q plus W, where U is internal energy of the system. So delta U is increase, yeah, or change in internal energy. Q is thermal energy supplied to the system or heat energy, and W is work done on the system. Complete figure 6.1 for each the process shown. Write down the symbol plus for an increase. The symbol minus to the indicate a decreases. The symbol 0 is not changed as the appropriate. 1. The compression of ideal gas constant temperature. Okay, U it's relate with temperature change. So if the constant temperature, so the temperature, so the U equals to 0. There is no change in temperature. There is no change in U. Yeah. Q, yeah, this is negative. Yeah. Why? Because this is 0, and if we put 0 uh, in this area, in this notation, yeah. So Q plus V, Q plus W means equals to 0. So we can say this is minus, this is plus. Why here plus? Because compression, yeah, compression they have in work done increases. So we can say this is plus, and because this is 0, this is minus. Yeah. And then the heating of solid with no expansion. No expansion, W is 0. Yeah. W is 0, it means the sign of delta U equals to the sign of Q. So the heating means it increases up the temperature. So delta U it will be increases also. So we can put here as the positive, and also this is positive also. Why? Because this is plus, this is 0. So it means Q equals to plus. The last one, the melting of ice at 0 degrees Celsius to give water at 0 degrees Celsius. Yeah, not ice less dense than water. Okay, okay. Uh, Melting ice on the, yes, melting they have Q as the positive. Yeah, Q as positive, and W is 0. Why 0? Because there is no work done. Yeah, there is only the energy required only for the melting from the solid to liquid. So if we put this as positive, W is 0, and then Q is positive, so delta U it will be positive also. That's the answer. Yeah. Okay, question 3. Don't forget to subscribe my YouTube channel. Yeah. Define specific latent heat of fusion. Oh, this is thermal energy required. Yeah, thermal energy or heat required to convert unit mass over 1 kilogram solid to liquid. Yeah, so there is with not change temperature. Yeah, yeah, because L. Yeah, latent heat of fusion or initial as the L equals to Q over M. Q is thermal energy or heat required, yeah, and then M is unit mass in 1 kilogram joule. Yeah. So, specific latent heat of fusion is the thermal energy of heat required to convert unit mass in 1 kilogram to solid, yeah, of solid to liquid. Okay, now B question. We have B question here. Yeah. A mass of 24 grams of ice at minus 17 degrees Celsius is taken from freezer and placed in a beaker containing 200 grams of water 20 degrees Celsius. Data for the ice and for water given figure 3.1. Yeah. On the ice, we have specific heat capacity as the 2.1 times 10 power 3. Yeah, this is specific heat capacity of ice. And then specific heat capacity of water is 4.2 times 10 power 3. Specific latent heat of ocean of the ice is 3.3 times 10 power 5. Yeah. And then water we don't have. Okay, the first question is calculate the quantity of thermal energy required to convert the ice at 15 degrees Celsius to water at 0 degrees Celsius. Yes, this is about ml, yeah, melting heat, yeah, energy required to warm ice, yeah. Oh, sorry, the ice need to increase until the degree Celsius temperature. So this is mc delta T, yeah. M of the ice is uh, 24 gram. Yeah, yeah. We change into kilogram divided by 1000, and this is specific heat of ice, and this is delta T. Yeah, when ice from negative 15 degrees Celsius rise up to 0 degrees Celsius, and then we have 756 joule. And also we energy required to melt ice. Yeah, melt ice is M times L. M 0.024 and then L is 3.3 times 10 power 5. We have 7,920 joules. So total energy is yes 1,700 joules. Yeah, around that. Okay. Now, assuming that the beaker has negligible mass, calculate the final temperature of the water in the beaker. Okay, the beaker is receive about the energy from the ice. Yeah. Yes. 200 gram of water on the beaker. Yeah. And then times with a specific heat of water 4.2 times 10 power 3, and his when the ice from 28 degrees Celsius goes down, yeah, into the T, yeah, T temperature at the uh, equilibria, yeah, equilibrium temperature, And the same thing with 24, yes, of ice rise up, yeah, after they change, after they uh, has passed as the water, yeah, with the specific of water, yeah, 4.2 times 10 power 3, and this is t minus 0 plus 8876, actually this one, yeah, or we round off 800, 8700, or 806, 8676 joule. So we calculate, this is about water, this is about ice. Water, yes, we have 14,444 equals to 940.8 T. So we have T equals to 15.77. Yeah, let's say around 16 degree Celsius. Okay, that's the question I. No question 4. Yeah. Yeah, don't forget to subscribe my YouTube channel, and so please share to the other. The electrical resistance of thermistor is to be used to measure temperature in the range 12 degrees Celsius to 24 degrees Celsius. Yeah. Figure 3.1 show variation of temperature measured degrees Celsius of the resistance of the thermistor. Okay, instead and explain the feature of figure 3.1 which show the thermistor has sensitivity variance of temperature. The sensitivity is about the gradient of creep. Yeah. Uh, Gradient of creep is measure of the sensitivity. Yeah. The gradient varies with temperature. Okay. At one particular temperature, resistance at the 2040 plus minus 20 ohms. Yeah. Determine the temperature in Kelvin to appropriate number decimal place. Yeah. Okay. This on the 2040 ohms is around 15 degrees Celsius. Yeah. So in Kelvin, this is something with 15 plus 270, yeah, degree. This is something with 288 Kelvin. Yeah, so this one. So 2040 here, yeah, same thing with in the 15 degrees Celsius. We change in degrees Celsius into Kelvin, we plus it with 273, yeah, yes, is equal to 288 Kelvin. Okay, I try to one number again, yeah, question 5, yeah. Let's see it, yeah. Use the kinetic theory of matter to explain why melting requires energy, but there is no change in temperature. Yes, on melting, bonds between molecules are broken or weakened. Yeah. Yes, or molecules further apart are able to slide over another. Yeah. Or kinetic energy unchanged, so no temperature change. Yeah. Potential energy increase or change, so energy required. Yeah. Yeah. Question B, define specific latent heat of fusion. Yeah. Thermal energy, heat rocket convert unit mass from solid to liquid. No temperature change at the normal boiling point. Yeah. Yeah. Then we know that Q equals to ml, so L equals to Q over M. On the C question, yeah. A block ice at 0 degrees Celsius has hollow its top surface as illustrated figure 2.1. Oh, they have hollow. Yeah. This is ice. Yeah. A mass of 106 gram, 6 gram water, 100 Celsius poured into the hollow. The water has specified the capacity 4.2 kilojoule per kilogram Kelvin. Yeah. Some of the ice melts. And the final mass water in the hollow 365 gram. Okay. Question I. Assuming no heat gain from the atmosphere, calculate a value in kilojoule per kilogram minus 1, yeah, for the specific latent heat of ocean of ice. Okay. Okay, thermal energy loss by water. Yeah, water they have 160 gram, something with 0.16 in kilogram. And this is about specific uh, of water 4.2 in kilojoule per kilogram. Then change in temperatures is 100 degrees Celsius. We have 67.2 kilojoule. And 67.2 kilojoule equals to ml. Yeah. So mass as the 365 minus 160 gram. Yeah, equals to 0.205 L. So L equals to 328 kilojoule per kilogram. Okay, one more question. In practice, heat is gained from the atmosphere during the experiment. This means that your answer to I is not the correct value for the specific latent heat. State and explain whether your value is 1 is greater or smaller than the correct value. Yes, this is more energy than calculate melt ice. Yeah, yeah, more energy. Yeah, than calculate is melt ice. So calculated L is lower than accepted value. Okay, thank you very much for watching my video. Don't forget to subscribe and also share to the other. Yeah, I think some student need this explanation. So share to the others, share to your friends, share to your student, or share to your maybe boyfriend or girlfriend. Yeah, thank you very much and see in other my video. Bye.